Hi everyone. So today we're going to be going through some of the questions from tutorial 1. We're not going to go through all of them. If you want to have a look at all the solutions, please take a look at the PDF that's been uploaded to Learn 2022. Okay, so we're just going to go through some of the important ones that you'll need to know. Okay, so question 1 was about finding the antiderivatives of certain functions. So let's take a look at 1.1. So we're given the function f of x is equal to cos x. If we want to find the antiderivative, then that's going to be capital F of x is equal to sine x plus c. So remember, we need to add the constant plus c whenever we're looking at the general antiderivative or the family of antiderivatives. And we can easily check our work. If we take the derivative of sine x plus c, we get back to cos x. So we know that that's correct. 1.2, we have f of x is equal to sec squared of x. Now this one we covered already before, so I'm just going to write the solution down. The antiderivative in this case is going to be tan x plus c. And then you can, again, take the derivative just to check your answer. Okay, 1.3. This was f of x is equal to 3x to the 4. So then the antiderivative would then be, well, we need, the exponent is 4, so we have to add 1 to make the new exponent 5, and then divide by 5. So we get 3 over 5 x to the 5. Okay, so we're just using that power rule that we derived for antiderivatives. Okay, 1.4. Here we have f of x is equal to 6x plus 4. Again, straightforward polynomial. We can just do it in parts. Sorry, for the previous one, remember plus c. Okay, so then the antiderivative in this case, what are we going to get? The old exponent was 1, so we add 1 to make it 2 and divide by 2. So we get 3x squared plus 4x, and don't forget the plus c. Okay, what about 1.5? Here we have f of x is equal to x root x. Okay, but this is not written in terms of a power, so we can't use that rule as is. But what we can do is write this as x to the 1 times x to the half. So we end up with x to the 3 over 2. Okay, now we've got a power that we can work with. So if we want to find the antiderivative, then the antiderivative capital F of x will then be, well, we need to add 1 to the exponent to make it 5 over 2, then divide by 5 over 2, but that's the same thing as multiplying by 2/5. Then we have x to the 5 over 2, and don't forget the plus c. Okay, so that's all the antiderivatives from question 1. Let's take a look at the next question, question 2. So 2.1, we're given a double derivative and we are asked what is the original function. So here we have f double prime of x is equal to 20x cubed minus 12x squared plus 6x. Okay, so now we want to find the original function. So first we can take the antiderivative to find the first derivative. And that's going to be 20 over 4. So that's going to be 5x to the 4 minus 4x cubed plus 3x squared plus c. Okay, if you take the antiderivative once, you go from the second derivative to the first derivative. Now we want the original function, so we need to do the antiderivative again. So here is going to be x to the 5 minus x to the 4 plus x cubed plus cx Now again, whenever we do the antiderivative, we need to add a constant. But in the previous line, we've added a constant c. So now we can add another constant d. Okay, let's look at the next one, 2.2. So we have f prime of x is equal to x plus 1 over root x, where f at 1 is equal to 8. So here we're given a bit more information. So we're given this bit of information here, and we can use this to solve for the constant that gets added during the antiderivative process. Okay, so we can explicitly solve for whatever that plus c needs to be. Okay, but first we need to do a bit more working on this first derivative, because as it is here, we don't have any nice powers that we can deal with. So let's rewrite this as f prime x is equal to x over root x plus 1 over root x. Okay, we've just separated the fraction out. But now that we've separated it out, we can simplify and write it in terms of exponents. So x over root x, that's the same as x to the 1 divided by x to the half. So we can rewrite this as x to the 1/2 plus 1 over root x is the same thing as 1 over x to the half, which is the same thing as x to the minus 1/2. Okay, so now that we've got the function written with nice powers, we can then use the power rule for antiderivatives. So f of x is going to be, so for the first one, we add 1 to the exponent to make it 3 over 2, then divide by 3 over 2, or we could multiply by 2/3. So we have x to the 3 over 2. For the second term, we add 1 to the exponent to make it 1/2, divide by 1/2, or that's the same thing as multiplying by 2. Okay, and then minus 1/2 becomes plus 1/2. And don't forget, we need to add c. But in this case, this plus c is not some arbitrary constant, but we can use this information to solve for c. We can solve for c. Okay, how do we do that? Well, we substitute in what we know. So we know f of 1 is equal to 8. So if I substitute x is equal to 1, I'm going to get 8 is equal to 2/3 1 to the 3 over 2 plus 2 times 1 to the 1/2 plus c. Okay, so 8 is equal to 2/3 plus 2 plus c. So 8 minus 2, if we take that across, we're going to get 6. And then minus 2/3 is equal to c. Then 6 times 3, we can write that as 18 over 3 minus 2 over 3 is equal to c. And so c is equal to 16 over 3. Okay, so we have solved for what c needs to be. So we can take this answer, substitute it back into what we started with, and we see that f of x is equal to 2/3 x to the 3 over 2 plus 2x to the 1/2. And instead of saying plus c, we know exactly what that has to be, 16 over 3. Yeah, and that gives us what our function needs to be. So whenever you get a question like this, where you're given some extra information on the side, for example, the function evaluated at some x value, or maybe the first derivative evaluated at some x value, you can use that information to solve for these constants that we have to add during the antiderivative process. Okay, so every time you have to add a constant, you can use that bit of information to solve for it. substitute back, and then that will give you your expression. Okay, let's take a look at the next question, question 3. And that was on the Riemann integral, or the limit of the Riemann sum. So let's do one of those just for some practice. So this is 3.1. We have f of x is equal to x cubed minus 6x. Okay, and in this case, we want to find the area from a is equal to 0 to b is equal to 3. So the interval from 0 to 3. Okay, so the first thing we need to do is those 3 pre-steps. So that is finding our delta x. So that's going to be 3 minus 0 over n. So that's 3 over n. Next, we need to find xr. So that's going to be a plus r delta x, or we can write that as 3i over n. Okay, because a is 0. And then lastly, f of xr is going to be, well, what was our function? It was x cubed minus 6x. So that's going to be 3i over n cubed minus 6 times 3i over n. And we can simplify this to 27 over n cubed, I cubed, minus 18 over n r. Okay, so we've just simplified that so that we can use it later on. Okay, so let's get to the main calculation of finding the area. So the area is equal to the limit as n goes to infinity, the sum from I equals 1 to n, f of xr delta x. Okay, so now we can substitute what we know. So this is going to be the limit as n goes to infinity, the sum from I equals 1 to n, f of xr, we just calculated that. That's 27 over n cubed, I cubed, minus 18 over n r. And don't forget the delta x, that was 3 over n. Okay, we don't want to forget that on the end. Okay, so now we can multiply everything through and separate out the sum. So this will be the limit as n goes to infinity. Okay, so 27 times 3, that's going to be 81. N cubed times n, that's going to be n to the 4. So we get 81 over n to the 4. And then the sum from I equals 1 to n of r cubed. Minus 18 times 3, that's going to be 54. N times n, that's going to be n squared. And then we have the sum from I equals 1 to n of r. Okay, like I said in the previous lectures, these summations here, so the sum from I equals 1 to n of r cubed, and the sum from I equals 1 to n of r, those can be replaced with their closed form expressions. In other words, we can write the limit as n goes to infinity, 81 over n to the 4. Okay, how else can we write the sum of r cubed? Well, we can write it as n plus 1 over 2, but all of this squared, minus 54 over n squared. And then how else can we write the sum of r? Well, we can write it as n plus 1 over 2. So we replaced the sum of r cubed with this term I'm highlighting in yellow. And we can replace the sum of r with this term that I'm now highlighting in yellow. Okay, so we've just done a substitution. So this we replace with this, and that we replace with that. Okay, so now that we've removed the summations, it's just a matter of algebra to simplify this out and then take the limit. Okay, so let's see how much simplifying we can do. this will be the limit as n goes to infinity of 81 over n to the 4. And then with the squaring here, we can write this as n squared, n plus 1 squared, all over 4. I've just squared all the terms, minus, and then for this term over here, I can do a bit of simplifying. This n in the numerator, I can cancel with one of the n's in the denominator. Okay, so I'm left with 54 over 2n, n plus 1. Okay. So what else can we do now? So this n squared for the first term, we've got n squared in the numerator, n to the 4 in the denominator. I can cancel that n squared, and I can cancel 2 of those. So I'm left with n squared in the denominator. Okay, so what do we have now? We have the limit as n goes to infinity of 81 over 4n squared. That's what's left over. And then we have n plus 1 squared. I can write that as n squared plus 2n plus 1. So I've just expanded that out. Minus, this is going to be 54n over 2n minus 54 over 2n. Okay, so I've just multiplied that inside there. Okay, so we can do a bit more simplifying here. So this will be the limit as n goes to infinity. So this first one, 81 over 4n squared times n squared, we're going to get 81 over 4. Okay, because the n squareds are going to cancel. And then for the next term, we're going to get 81 over 2n, because the 2n divided by the 4n squared is going to give us 2n in the bottom. And then the last term, we're going to get 81 over 4n squared minus. So for the next term, we can cancel this n with that n. So we have minus 54 over 2, and then minus 54 over 2n. Okay. So that's all the simplification we need for now, because if you notice, the terms with the n in the denominator, they are going to go to 0 as n goes to infinity, because these fractions are going to get smaller and smaller as n gets bigger and bigger. So in the limit, they're going to go to 0. So this one's going to go to 0, this next one's going to go to 0, and this last one will go to 0. Okay, so we can just leave those out. Okay. So this is going to give us, sorry, we've already done the limit there. So we're going to have 81 over 4 minus 54 over 2. That's just a little bit of arithmetic. We're going to end up with minus 27 over 4. Okay, so that's our answer for the Riemann integral. Okay, let's take a look at the next one, just as a bit more practice. Yeah, and then as always, if you do have questions, please just email me, or you can put a message on our class WhatsApp group. Okay, so let's take a look at 3.2. So we have f of x is equal to 1 plus 3x. And then we have a is equal to minus 1 and b is equal to 5. Okay, so that's the interval that we're working on. So we need to do the little pre-steps. So delta x is going to be 5 minus 1 over n. So that's going to be 6 over n. xr is going to be a plus r delta x. So that's going to be minus 1 plus 6i over n. And lastly, f of xr is going to be 1 plus 3xr. So that's going to be 1 plus 3 times minus 1 plus 6i over n. Okay, and we can simplify that because we're going to get 1 minus 3. So that's going to be minus 2. And then 3 times 6i over n, that's going to be 18i over n. Okay, that's an I over there. Cool, so with all of that done, we can then substitute this into the formula. Okay, so remember that the area under the curve is given by the limit as n goes to infinity, the sum from I equals 1 to n, f of xi delta x. Okay, and we know all of these from the previous calculations. So we're going to have the limit as n goes to infinity, the sum from I equals 1 to n, f of xi, we know what that is. That's minus 2 plus 18i over n. And delta x, that is 6 over n. That's an I over there. Okay, so now we can multiply everything out and then simplify. So that's the limit as n goes to infinity, the sum from I equals 1 to n. If we multiply this out, we're going to get minus 12 over n plus 108 I over n squared. Okay, so exactly as we did before, we're going to separate this out and simplify each of the summations. So this is going to be the limit as n goes to infinity, minus 12 over n, the sum from I equals 1 to n of 1, plus 108 over n squared, the sum from I equals 1 to n of r. Okay, so now we've got these two summations here. And this one over here. We can now replace these summations with their closed form expressions. So here, this is the limit as n goes to infinity, minus 12 over n, and then the sum from I equals 1 to n of 1, that's just going to be n, plus 108 over n squared, the sum from I equals 1 to n of r, that is n plus 1 over 2. Okay, so let's just highlight that, this and this. So we replaced the first summation with n, we replaced the second summation with n times n plus 1 over 2. Okay, so now it's just a matter of algebra, and then we can finally take the limit. So limit n goes to infinity, n over n, they cancel, so we just left with minus 12, plus 108 divided by 2, that's going to be 54. If we expand this bracket out, we're going to get n squared plus n divided by n squared. Okay, so that's going to be the limit as n goes to infinity, minus 12 plus, and then we can write this as 54, 1 plus 1 over n. Okay, so this will be the limit as n goes to infinity, minus 12 plus 54 plus 54 over n. Now, this last term has an n in the denominator. So when we take the limit as n goes to infinity, this denominator is going to get very, very large, which means the fraction is going to get very, very small. So in the limits, this is going to go to 0. So we're just left with 54 minus 12. So we have a final answer of 42. Okay, so I think that's it for today. Please look on Learn 2022 for the full solutions. So I wrote them out and they're available in a PDF. If you do have any questions about those, please don't hesitate to email me or post a message on the class WhatsApp group. Okay, I'll see you in the next lecture.